Okay, guys, if you have not taken lecture 21, lecture 20, lecture 21, lecture 21 is new, totally new, and lecture 22, please come here to take yours. Some students have already taken 2020 and 20 and 22 already, but 21 is totally new. If you have taken 2022, you don't need to take it again. But 21 is the new. Last time I forgot to print them out. We talk about these composites. Composites, there are several important concepts. For example, this is we have talked about this is the thermoplastic and thermostats, and we have talked about this is the chain entanglement and chain station and shear yielding and creasing, and we have talked about several models here. And so even though, as I said, even though these models, I will not test your understanding of these models, but if I test your understanding, if we ask you some questions about these concepts in the final exam, and you still be able to come to this is lecture 20 to find the solutions. Okay. Today we are going to continue our talk. This is composites. We will talk about the composites. First, on the fatigue, and if you have the take machine design class with me, you guys did not take the computer-aided engineering, right? Okay, so maybe we need to have this course back.
Oh, we did take like a SolidWorks class.
SolidWorks?
Yeah, which is like a version of CAE.
Well, SolidWorks, you mean the software, right?
Yeah.
How you use the software?
For modeling.
No, I'm not talking about it. CAE, computer-aided engineering, that is mainly focused on the elasticity series, not for modeling. Modeling, we have CAD, computer-aided design, as a different. I will talk with the chair and to see if we can get this course back, because I found that some students are not familiar with the stress components and the strain components, and also kinematic equations, equilibrium equations. This is and other equations. But here we talk about fatigue, okay? Fatigue mechanism, and we have chain station. We talk about chain station. Chain station means that the chain is going off from the major body. And the second one, and the hysteresis, the heating. What is the hysteresis? I'm very interested in this hysteresis. This is very important concept. So chain station is brittle, and chain station easy to occur. Chain station means that the bonds between atoms are broken. So this is the chain station. What is the hysteresis? Michael, what is the hysteresis?
Like a way of showing the overall function, what you're looking at.
So in the mechatronics, I introduced the hysteresis when we talk about the sensors, right? You still remember? So that's the hysteresis. Hysteresis is very the common concept. It's not just in mechanics, but also for the sensors. What is the hysteresis? Hysteresis means that if you apply the load, you apply the load this way, right? So this is epsilon and sigma, and then at some point, and you just release and this, you just remove this load. Remove this load, so this guy come back to the original point, original starting point, and however, and so this loading and unloading, we have different paths. So different paths. So this is the area, shaded area, enclosed by these two different parts. So this is a phenomenon is called hysteresis. So this area is the energy consumed. In the mechatronics class, when I talk about sensors, right? We'll talk about sensors. So this is one axis. So this is a physical quantity, and so this is the measurement you get, right? The measurement you get when this is the signal amplitude goes up, it goes this way. When you release, when you remove this signal, and it goes down in different paths. So in that sense, it is also called hysteresis. Alright, here this is the same, very similar the concept, but they're talking about the same thing, different paths, loading and unloading. So this is usually, and hysteresis involves the energy consumption. And how you can see the energy consumption when you do these kind of things, and you will see the material feels hot, feels warm. So this is hysteresis becoming tougher, and also viscoelastic and deformation, yield at crack tip. Visco, as the name suggests, visco. What is visco, guys? Visco means just like fluid-like, right? Visco, fluid-like, and viscoelastic. Elastic means that this guy can come back to the original point. So here, so this is plastic deformation. That is viscoelastic deformation. That is hysteresis. Plastic deformation. Last time I showed you this diagram, sigma epsilon. We go up. So this is a linear elasticity, and then after the union point, so we have this one increases slowly, and then if you come here, so this is still hardening. Okay, you can see why it's called hardening, and because the yield strength is improving. And so at this point, if you remove the load, and you will have this kind of paths, and that means this one and this one. And these two lines, they are parallel to each other. But, so this one, you remove the load, and finally you will get a point here instead of this original point. So this is the residual. So this is the residual strain. It's called plastic strain. It's a permanent deformation. Any questions, guys? So the crack tip, if it is a fatigue load, the crack tip region in a polymer and subject to cyclic loading may rise to well above TG. Can somebody tell me what is the TG glass? Is a glass transition the temperature? What is the TG, guys? Can somebody tell me? I want you guys to interact with me. What is the TG? Can you just look at your lecture notes? TG means the glass transition temperature. It is the temperature above which the movement of these atoms, molecules are restricted. So this is called the glass transition temperature. So resulting in the local melting and the viscous flow of the material. So if you apply this is the fatigue loading. So this is about the fatigue. What I want you guys to know is on how to interpret. So this is hysteresis. If I ask you what is a hysteresis in mechanics, and you should be able to use this diagram and then use your own words to tell me what is a hysteresis is. Good? Questions? So no question, and we move on to next one. Is a fiber reinforced plastic composites, and so this is fiber reinforced plastic composites. Some people use the continuous fiber, some people use the chopped. The chopped fiber is a very small fibers. chopped, I mean the cut. Continuous fiber, reinforced plastic, however, have also tropic mechanical property that lead to unique failure mechanisms. For example, delamination and microbuckling. So I'm going to talk about this. So delamination and microbuckling. So first, we talk about orthotropic. What is orthotropic? Orthotropic, it has three systematic. This is the systematic, the plane, and with respect to the material properties. So this orthotropic is a unique, and also delamination and microbuckling, and might be happening. So. So we can design the material property, okay? Because these composites usually contain a matrix material, and then you have some reinforcing. This is the reinforcing things. For example, here, this is fiber, continuous fiber. So you can design these material properties. You can have high strength and weight ratio, or high stiffness and weight ratio. So these composite materials usually consists of a matrix. Matrix is the major material, okay? The main material, and then you just have some reinforcing constituent. And for this case, we have fibers. For this one is continuous fibers. As I said, we might have the chopped fibers. Okay, these are chopped fibers. Chopped fibers. So this is a very small, very small. These fibers chopped. You just put these chopped fibers, mix the chopped fibers with this matrix. So matrix, we talk about polymer, right? In last class, the polymer we have two big categories of polymers. So one is called a thermoset. For thermoset, is a cross-linked polymer. And cross-linked polymer means that this is some of this is a very, very long chain molecule chains, and they are cross-linked with one another. As a result, a thermoset is stiffer and strong. Another polymer is a thermoplastic. A thermoplastic is a linear polymers, the branched polymer. So we have backbone molecule chain as a backbone. Then on this backbone, we have some branches or just only this backbone. As a result, thermoplastic, they usually do not they are not very stable. Fibers. Fibers, and people use glass fibers. This is glass fibers. They are used in early stage many years ago. Use glass fibers. Glass fibers usually is white. A little bit brittle. Glass fibers a little bit brittle, but now recently, in the recent decades, people use carbon fibers, and carbon fibers is brittle. Right, so these glass fibers is a little bit brittle, but carbon fibers is more brittle. So this is fibers, carbon fibers, and this is glass fibers. So this is aramid. The aramid, known as the trade name Calva. So this is another fiber, okay, yellow fiber, high strength fiber is very, very tough. So aramid is another fiber. And so we can see the fibers, after we build the fibers, we can find that the material in fiber form is much tougher. Can somebody tell me why? And when you use the same material, however, if you fabricate this in the fiber form, why this fiber is much tougher than a bulky material, even though they are the same? Can somebody tell me? Huh? Why this is the same material? And one is that I have a bulky material. One is that we'll have the same, I have the fiber. Why the fiber is much tougher? because the fiber, if we build into the fiber, and we can minimize the fiber because the cross-sectional area is very small, right? So we have relatively very small fraction of the defects. You understand this? Then it's very, very tough. However, if for bulky material, we have a lot of defects in different locations, in different orientations. As a result, the bulky material will be much weaker when compared with the fiber, even though they are made of the same material. So fracture mechanics is used for the homogeneous material, right? So you should know that the components are inhomogeneous, and they have many micro cracks. We call this a crazium. So can somebody tell me what is a homogeneous material? What is an inhomogeneous material? Who can tell me, Carlos, what is the homogeneous material?
Isn't that like all the properties are the same throughout?
Okay.
All the properties are the same, like through the material.
Yes, right? Yeah. Homogeneous means that this material for different locations and the material properties are identical. This is a homogeneous. Inhomogeneous is opposite, and some area they have different mechanical properties. The homogeneous and isotropic, this is two different concepts. So homogeneous and isotropic. Carlos, you answered the first question correctly. Now I want to ask you this one. What is isotropic? Huh?
I can't remember.
Oh.
Isotropic.
Yeah, isotropic, iser. What is iser? When you see this is the prefix, what it comes into mind in your mind? Michael, what it comes into your mind when you see iser? Yeah, I'm asking you, Michael. Iser means something the same, right? So isotropic means that the material properties and for one location, for any generic location, mechanical properties are the same in all directions. Okay? Isotropic and homogeneous. And they looks very same, but they are different. This guy talk about orientation. For one point, homogeneous is talking about location, different locations. So usually for simplistic, and when we talk about this series, and we talk about homogeneous and isotropic material. Right? So this is to simplify all these things. So you can see the delamination. Delamination is, as the name suggests, delamination means that, and suppose we have composites and we have different ply, okay, different plates. We just glue these plates together. And the delamination means that when you apply the load after some time, and so this is, you can see these are two layers, they separate. So this is called delamination. Right? This is called delamination. And for this delamination, for in these coordinates, and we assume, so this is a three, the stress components in the z direction are equal to 0. Xz, Yz, and tau zz, and all of them are equal to 0. And also, for this is the delamination, second one is microbuckling. So for this one, you can see microbuckling. You know buckling, right, guys? Buckling? Buckling means that if you have a standard beam, if you then you apply this compressive loading, right? And then this guy, at some point, and this guy will become unstable. This is called buckling. The buckling, microbuckling means that if you have compressive loading, so the continuous fibers within this matrix material, and they buckle, and they buckle, this is called microbuckling. You understand, guys? Microbuckling is talking about the buckling for the this is the fibers. So here another buckling. This is a buckling delamination. So you have two layers. This is the two layers oriented this way, and then you apply the load. So because of buckling, so this layer and this layer, they separate. So this is called buckling delamination. Delamination, it means that the separation of adjacent the layers. The buckling in here means because you apply the load. So this is the one thing. Second thing is cross pie. And cross pie, you can see this is the laminate. This is one laminate. So for this laminate, we have 45 degree. The fibers are oriented in 45 degree. And for this supply, for this layer, and the fibers they are oriented in the negative 45 degree. So you want then we glue them together. So this is the equilibrium equation. Right? So this is equilibrium equation. And for this case, this is system symmetric layout. A symmetric layout, we can see what I'm talking about. You can see this supply, for this layer, the fibers are oriented vertically. We call this is 90 degree. Right? For the fourth one, and for this supply, and we also the fiber, and also they are oriented vertically. That means the first one and the fourth one, and they have the same orientation regarding the fibers. But for the second layer and third layer, and the fibers, they are oriented horizontally. Right? So these two guys in sandwiched. These four guys, they are sandwiched together. So this is the first layer, fourth layer, and this is the second layer and the third layer. So if we look at this one, we sandwich and these are four these plies together, and then we take a set row, we will have this. So this is 0, so this is 90 degree. Oh, okay. So you can see this is so this is 0, or this is 90 degree. And it does not matter. It depends on how you define it. So this is the set view, guys. Right? So when loaded, delamination always starts from the edges and the corners. When loaded, if you load this way. And so this is original configuration. So this is a curve is a final configuration. So you can see, so this is the layers, and they are separating each other. They separate each other on these two ends. On this end, they separate. On this end, and they also separate. Only in the middle, and they might still contact each other. So this is called delamination. So compressive failure, compressive failure, and we know that, and for metals, and we are very, very familiar with the metals, and for metals, the tensile strain and the compressive strain, and failure, I'm talking about failure, and failure strain, and they are identical, right? And so for metals, for the metals. However, for composites, the tensile strain and the compressive strain, they are totally different. They're different. Questions? Because composites, they are much more complex than the metals. For the metals, compressive and tensile, a lot of mechanical properties, we can treat them identically. But for composites, no. For composites. Questions so far? Michael, do you have any question? No, Josh? Okay, and then we talk about the buckling. Who have taken the machine design with me in this room? Casey? Michael, you took the machine design with me also, right? Josh? No? Supporter? Carlos? No machine design? Okay, in machine design, I talk about this is the buckling. The buckling means that suppose we have a very, very long this beam, we can call it a beam or column, and then you just compress it, and this compressive loading, and we have this equation. Okay? So this equation is used to calculate the P and which this allowable P. So P divided by A using this equation, we have this I, okay? I is error mode inertia. I equals the A is cross-sectional area, and rho is, and we call this the radius. And so this radius, and you can see, put it here, if we put this equation rho inside, and so we can introduce another, this is concept, L over rho. So this one is called the slenderness ratio. And this is used to measure on how slender this beam is. Not just the length. Why is it only length? If we just take care of the length, sometimes we might be misleading. Why? Because even though the length is very long, but if the cross-sectional area is huge, still we will not have the buckling problem, right? However, on the contrary, if the length is not very, very long, but the cross-sectional area is very, very tiny, but still, even though it is so long, but if the cross-sectional area is very, very small, we still have the buckling problem. So that's the reason we introduced this slenderness ratio and to measure the ease of this guy to be buckling. So we have this equation and we use the P to calculate. Then here, so this is this equation, the strength. When the P, right? When the P is greater than the strength, and the buckling occurs. And we use this equation to calculate the P, and then we just check this diagram. If we have the slenderness ratio, and we also check if the P for the same slenderness ratio, if the P calculated is higher than the strength in this diagram, that means buckling occurs. Does that make sense, guys? Are you following me? Okay. Okay. So this is a buckling, and this beam does not have the support. And so some people for the real composite, okay, if we put the fibers inside, this is a matrix material. Because we put this guy inside the matrix material, and so we just suppose, so this fiber is supported, right? So this is supported because of matrix material. So these people and come up with this model. The sigma C is a critical strength. It equals mu LT, right? Plus pi square EF VF R over L. L is a length, R is a radius. So mu LT is longitudinal and transverse the shear modulus, and this guy has the same unit as sigma C. VF here is a volume fraction of fibers. You know volume fraction, right, guys? Volume fraction of fibers. Let's suppose you have a matrix material, and then you put some fibers inside. And what is the volume the fibers take? And then the whole volume of the matrix. Then you just have volume fraction of fibers. Then the EF is Young's modulus of the fibers. So we can use this equation and to calculate the critical strength of this material. You understand, guys? So this model, okay, there is one observation. So this model over predict This is the strength by a factor of 4. Can you underscore this one? So this composite is too optimistic. This one is usually over predicts the strength of the material of the fiber by a factor of 4. So this one for elastic only. So this guy might have the global buckling. Global buckling means that here, this is global buckling. And also micro buckling. Micro buckling is only talk about this is the buckling of the fibers. Questions so far? So this equation, okay, I will not ask you guys to use it, but if there is a need, and you can just come back and to use the equation. How to do the composite material, maybe you can usually use the abacus or ANSYS to model. So questions so far? Then we talk about no questions. So maybe I can give you a small quiz in the class. I just want to engage you guys. Give you 10 minutes to just summarize what you have learned. So this is what I learned in the seminar. How can I engage my students? Every kind of 15 minutes, give them 2-minute small questionnaire to answer. That's done. Okay. Okay, so then we talk about notch strength. Notch, as a name stress, we have this is a hole here. We just use a hole. Normal stress, notch stress. The stress, this SCF means stress concentration factor. And so if the stress concentration factor equals 3, and the reduction in strength is about 1/3. Why this one is true? Can somebody tell me? I would ask you guys to write this down, okay? SCF, it means stress concentration factor. Whenever you have some defects on the material, and you will have stress concentration factor. The higher the stress concentration factor, the bad the material will be, right? Because if the stress concentration factor is very high, and then reduction of the strength will be about 3, just the reciprocal of this SCF times the ultimate strength of your material. So strength depends on the size of the hole. We can still use the dimensionless analysis and to check. And here we use the sigma ij. Right? Sigma ij can be written as a function of Young's modulus, Poisson's ratio, the hole diameter. Here is the hole diameter. L is the length, and the magnitude of the stress, the remote stress. So we can use this one. And then, we can just, because sigma ij and sigma remote, and they have the same unit, the Pascals or KSI, PSI, and so we can just divide everything here by the sigma remote, and also by this is L. Right? But here, because sigma ij does not have the length, so we can just divide sigma ij and by this is sigma remote. That will be okay. And so we can get this, make this guy dimensionless. So Young's modulus has the same unit as the remote, sigma remote. Nu is this itself is dimensionless. A is length, and we just divide A by L. R, and R is how far it is from this is the from this hole, and this is RL. R divided by L and theta ij, and theta ij. Where theta ij is the orientation. So what is R and what is, so here, so this is my hole. And suppose here. So this is the X, so this is origin, and here is a Y. So this is my generic point. So here is R, so this is theta. Location. So for any point, I can have red R is a radian, the distance between the point of interest to the crack I will not use the crack, and to this hole. And theta ij is orientation. However, if the L is very, very huge, if L goes infinity, so we can have sigma ij, we just want to know when R equals A, right? R equals A and theta equals 0 in this area. I'm sorry. We say this is X. This is Y. So this is A, right? The radius of the hole. So when R equals A at this point, so this is the hole. And theta equals 0 in X direction. And I want to calculate the stress at this point. And then I can have, this is F, okay? So E sigma remote, dimension is, and this sigma ij. And so this one can be written as, it is a function of this one and this mu. And because L is very, very huge, this goes to 0, and so this goes to 0. And only have is sigma ij is orientation, sigma equals 0. So this one can be written as this. So I only have this variable and this variable. So you understand this? Where is A and where is R? Because I said L is very, very huge. If L goes to infinity, so this one is almost 0, this one is almost 0. Also here I specify theta equals 0, orientation equals 0. So as a result, sigma ij equals 0. As a result, for this point, I only have this gamma. This is a nu here. So then I can have this sigma ij on the edge, and when R equals A and theta equals 0, and divided by E equals F nu as a function of this is Poisson's ratio. So you can see this figure, guys. So this figure for a small hole and a large hole. So here is R over A, okay? So this is x-axis R over A. So here is a SCF, stress concentration factor. So here is 3, and then goes down just like a parabolic. For this is the small hole, and for large hole, it also goes down. You can see this one. So here is a large hole, and here is the small hole. And so from here, we know that it goes this way for small hole, it goes that way for large hole. And we can see that even though the maximum stress concentration factor are equal to each other for these two cases, but for large hole, and we have a bigger the distance, bigger interval that have higher, this is a stress concentration factor. So this is more dangerous, right? So this is more dangerous. So you can see there is an observation. Although the peak stress is the same for both holes, the stress concentration effects of the large hole acts over a wider distance, as I said, wider distance. Thus, the volume over which the stress X appears to be more important for large hole. Questions? So dimensionless analysis is a very powerful tool that we can use. No question? And then we take a look at the model. Okay, so this is the model, and there are some observations. So Whitney, Newismer proposed the model, and this average criteria. And so from this sigma bar, okay, if the sigma bar is equal to unnotched sigma, if sigma bar equals the unnotched sigma, and so we say it fills. So what is the sigma bar? And sigma bar is the sigma yy, okay, and sigma yy, and then we do the integration of sigma yy over x from 0 to a0, then divided by a0, and then we compare this value with unnotched sigma. If this one equal to each other, so we say this is a very critical state. It is going to fail. So a0 is a 4 millimeter to 8 millimeter. It depends on the materials. So this is one criteria. And second criteria is a point criteria. And it says that you can have a distance in front of when theta equals 0, and you can just select d0, which usually equals 1 millimeter to 3 millimeter. At that point, if the stress is equal to the unnotched stress, and then we say this material fails. Not fails, it is the propagates. We say it fails. Questions so far? So these we have two models. One is average criteria model, and one is a point criteria model. So how accurate it is dependent upon the materials. Okay, so so if you have a really engineering applications, and I would suggest you use a VM to build the model or to the experiments. So these models, they have been used many years ago. And then there are several observations. The LEFM to be valid for sharp crack in a composite panel means this is a material, the following conditions must be met. Right? So this might be tested in the final exam. First one, the fiber spacing must be small compared to the size of the singularity zone. Otherwise, the continuum assumption is invalid. So this is one first assumption. Second one, nonlinear damage must be confined to a small region within the singularity zone. So this is two conditions that must be met if you want to use LEFM to solve the problem. So there are two observations also. Fracture mechanics is not suitable for composite materials. Whitney Newismer is good for composite materials. You cannot use fracture mechanics. However, Whitney Newismer model, this guy, either one, either average criteria or point criteria, you can use either of them and for these composites. So composites, how to say? Composites, they are difficult to handle because the different people, different research teams, and they built different composites, and you need to be very careful. All right? Questions? So this is what I have today, and this is what I have today. And any questions before we end today's session? No question? So can we have the very quick quiz next week? But I want you to know these as the facts, okay? I want you to know these facts, if there's a need, come back to get these solutions, to get these answers.